Welcome to the debate. Imagine, just for a moment, that someone hands you a beautifully crafted ceramic teapot.
Okay.
The glaze is flawless, the handle is perfectly ergonomic, but there's a catch.
There usually is.
The spout is pointing backward, like directly over the handle.
Right, so it's a brilliant piece of engineering that is completely and utterly unusable. I mean, if you try to pour it, you'll just burn your hand.
Exactly. And today we are looking at the core intellectual tension in enterprise network architecture. This is based on the foundational design principles and case studies found in advanced routing and switching material. When we design for high availability and scalability, we are constantly forced to choose between two competing philosophies.
Right, the classic trade-off.
Yeah. Do we prioritize predictable simplicity, or do we embrace robust complexity? I take the side of predictable simplicity. My position is that every time we add a complex protocol interaction, whether it's, layer 2 spanning tree loops, first hop redundancy, or intricate route redistribution, we introduce fragility. We essentially end up building that backward-pointing teapot. The advanced features might technically work on a whiteboard, but they prevent the network from functioning predictably during a crisis. So I argue we have to limit our fault domains by stripping away unnecessary moving parts.
Well, and I take the side of robust complexity. Look, simplicity is a beautiful concept, but it is a luxury that modern enterprise networks they simply cannot afford. There is a fundamental principle in network design, which is that robustness requires complexity.
But does it always?
I'd say yes. If you want a highly available system, you cannot rely on a single path or a single point of failure. The moment you add redundancy, you add complexity. It's like the old design adage goes, 2 is company, 3 is crowded.
Right.
If you avoid advanced feature tuning just to keep your topology simple, you are going to end up with stranded bandwidth, suboptimal traffic flows, and honestly, a complete failure to meet basic business requirements, things like seamless virtual machine mobility.
See, the problem with that approach is the butterfly effect. In a complex design, you summarize a prefix in one area, and suddenly you cause suboptimal routing in a completely different part of the network. Every new feature you enable introduces these unpredictable state machines interacting with one another.
I wouldn't call them unpredictable.
Well, they can be during a failure. When a core link goes down, I want a clean mathematical recalculation. I definitely do not want a cascade of protocols trying to elect a new master while dropping packets. That is exactly why I argue for pushing layer 3 routing as far down as possible, specifically to the access layer, and maintaining a single interior gateway protocol domain whenever physically possible.
I mean, I understand the desire for a clean mathematical recalculation. I really do. But a well-designed network is inherently complex. When orchestrated correctly, the output is resilience and efficiency that a stripped-down design could just never achieve.
Even with the added risk?
You can't just remove features because they require mastery. Take gateway load balancing protocol, for example, or multi-level ISAS and OSPF designs. Are they mathematically complex? Absolutely. Do they require careful architectural tuning? Yes.
Highly careful.
But they are absolute necessities if you want to maximize resource utilization and actually survive multiple concurrent failures. A simplistic design that wastes half your uplinks because the architect was afraid of protocol interaction isn't a good design. It's a severely inefficient one.
Okay, well, if we mandate simplicity, we have to look at where the network begins, right? The access layer. This is where users and devices connect, and it's the site of a massive architectural divide. Do we use layer 2 looped designs or layer 3 loop-free routed access designs?
The eternal debate.
Right, and I strongly advocate for routed access. By configuring layer 3 routing directly on the access switch, we completely eliminate spanning tree protocol between the access and distribution layers. There are no blocked links to manage it all. Furthermore, there is no need for a first hop redundancy protocol like HSRP because the access switch itself is the default gateway. It's clean.
But you are designing in a vacuum there. Layer 2 loop designs aren't just some legacy hangover. They are strictly mandated by physical business realities. In the modern data center, virtual machines must move seamlessly between physical hosts to balance compute loads.
Right, live migrations.
Exactly. For a VM to retain its IP address during a live migration, its VLAN must span across multiple access switches. You see the exact same requirement in campus networks, where widespread wireless LAN requires seamless roaming across access points without dropping a VoIP call.
Yeah, I know the mobility argument.
Look, if you terminate layer 3 at the access switch, you break that mobility. The subnet ends at the switch, and the device has to request a completely new IP address when it moves. You just can't do that to the business.
Look, I see why you think that, but let me give you a different perspective. Why manage the precarious interaction between the spanning tree root and the HSRP active node when you can just route from the edge? Let's explain the mechanism of what actually happens in a stretched layer 2 topology if those protocols desynchronize.
Okay, let's play this out.
Let's say your spanning tree root bridge is on distribution switch A, but your HSRP active gateway is sitting on distribution switch B. Suddenly, the interconnection link between those two distribution switches becomes a transit path.
Right.
Traffic from the access layer takes a multi-hop layer 2 path, congesting your inner switch link just to reach its default gateway. And what happens when a switch reboots?
Well, you tune the timers.
But if you don't perfectly tune them, if HSRP preempts and declares itself active before the switch has established full layer 3 connectivity to the core, it black holes all the traffic. You have to manually tune HSRP preempt delays to be mathematically greater than the switch's boot time just to keep it stable. Why take on that fragility?
Because you are sacrificing bisectional bandwidth if you don't. Yes, legacy spanning tree blocks a link to prevent a loop, meaning you leave half your uplink capacity just sitting idle. But you don't have to use legacy spanning tree.
You're going to bring up MST, aren't you?
I absolutely am. If you embrace the complexity of multiple spanning tree, MST, you can unlock that bandwidth. MST allows you to group dozens of VLANs into a single spanning tree instance.
Right.
You keep distribution switch A the primary root for instance 1, which carries your odd-numbered VLANs, and distribution switch B the primary root for instance 2, carrying your even-numbered VLANs. Now you have active utilization of your physical infrastructure. Both uplinks are forwarding traffic. You tune MST for scalability, and you gain massive throughput that a strict routed access design simply sacrifices.
MST tuning is incredibly operationally cumbersome. You are manually mapping VLAN instances to physical paths in a configuration file. If an operator makes a single mistake mapping those instances during a 2 a.m. maintenance window,
Which is why we have change management.
the resulting layer 2 loop will broadcast storm and melt down the entire switching fabric within seconds. But, okay, for the sake of argument, let's concede your point. Let's assume that business requirements, like legacy host overlays, force us to stretch layer 2 across the campus.
Which they often do.
Right. But we suddenly inherit a massive problem. How do we route out of that stretched VLAN without creating a bottleneck? That forces us to confront gateway optimization. And this is exactly where I see engineers constantly outsmarting themselves by reaching for GLBP.
Oh, I strongly disagree. Gateway Load Balancing Protocol is a highly effective tool. It does exactly what HSRP cannot natively do. It provides true network-based load balancing without requiring the client to do anything differently.
On paper, maybe.
e.g., manages multiple virtual MAC addresses. When different hosts on the network send an ARP request asking for the MAC address of their default gateway, the AVG acts as an intelligent dispatcher.
A dispatcher.
Yeah, it responds to host A with the virtual MAC of distribution switch 1. It responds to host B with the virtual MAC of distribution switch 2. You are mathematically ensuring both uplinks are actively processing data plane traffic. I mean, how can you argue against getting the full value out of the hardware you purchased?
Because your argument relies on a perfect, uniform distribution of clients, which ignores edge cases that completely break the protocol's intent. Let's look at the Internet Edge case study from the source material. Instead of hundreds of PCs, you have a massive enterprise firewall sitting below your two internet gateway routers.
Okay.
The firewall has a default route pointing to the GLBP virtual IP. Let's replace your dispatcher metaphor with something mechanical. GLBP is like a traffic cop standing at an intersection with two identical bridges.
Sure, I follow.
The cop points the first car to Bridge A, the second car to Bridge B, ensuring both bridges are used. But in the firewall edge case, you don't have multiple cars. You have one massive bus.
Meaning the firewall is acting as a single appliance, proxying all the traffic?
Exactly. The firewall performs a single ARP request. The traffic cop, the active virtual gateway, responds with a single virtual MAC address belonging to router 1. The firewall takes that MAC address, caches it in its memory, and doesn't ask again.
Right, until the ARP timeout.
Which could be hours. All outbound traffic for the entire enterprise is now polarized to a single link. Anyway, GLBP's entire load balancing mechanism falls apart because it fundamentally relies on multiple clients sending multiple discrete ARP requests.
Look, that is a specific corner case regarding single appliance transit. It just means GLBP is the wrong tool for that specific block of the architecture, not a failure of the protocol itself.
But it highlights the danger of hidden complexity. Trying to be too smart with GLBP backfires because the mechanism is obscured from the operator. Ironically, the simpler HSRP is vastly superior here.
HSRP is active standby, though.
Unless you engineer it. To get active-active forwarding from that firewall, you don't use GLBP. You use HSRP, and you configure two distinct simple groups. You set router 1 as active for group 1, and router 2 is active for group 2.
Then on the firewall, you explicitly split the default route statically. You route half the IP space to the HSRP Group 1 IP and the other half to the Group 2 IP. You manually engineer the egress traffic policy cleanly. You avoid the ARP caching polarization entirely. Predictable, transparent simplicity wins.
Wow. Okay. I would heavily contest the idea that manually splitting a default IP route in half and managing two separate HSRP groups is simple. That is manual traffic engineering. You are just manually doing what GLBP attempts to automate, which introduces its own human error risk.
But the risk is visible.
Fair enough. I will concede your point on the firewall ARP cache limitation. It's a valid edge case. But once we secure that gateway, the traffic enters the routing core. And the moment traffic crosses from one routing domain to another, we face the necessity of route redistribution. And I think your philosophy of avoiding complexity hits a brick wall right here.
Route redistribution is the most dangerous mechanism in enterprise networking. I take a hardline stance against it whenever humanly possible. The source material is quite explicit on this. It says, if you can avoid, don't use redistribution. Managing it can be really complex.
It says can be complex.
Redistribution is the undisputed leading cause of catastrophic routing loops, and the mechanism of why it fails is vital to understand. Routers do not redistribute routes between protocols directly. They don't take a route from, say, OSPF and hand it straight to BGP.
No, they use the RIB.
Exactly. They pull routes from the routing information base, the RIB. The RIB is the mathematical table where the router decides its absolute best paths. If a route isn't installed in the RIB, it doesn't get redistributed. This creates massive race conditions during link flaps where stale routes are injected back into a domain.
So what's your solution?
I advocate for the FastNet approach. The case study shows a fictitious service provider migrating entirely from OSPF to ISIS just to avoid running two protocols and dealing with the redistribution boundary while deploying IPv6. A single protocol domain is safe.
The FastNet migration is a luxury. Have you considered environments where running a single protocol is administratively impossible?
Like where?
Let's look at the EIGRP and BGP case study from the text. You have an enterprise customer using an MPLS VPN as their primary WAN path. That MPLS link relies on BGP, which is controlled by the service provider.
Right.
The enterprise is using their own DMVPN, a dynamic multi-point VPN, as their backup path, which runs EIGRP. You physically cannot run a single protocol here. The provider controls the MPLS side, and you control the DMVPN side. You have to redistribute between them.
And that exact boundary is where networks melt down during a failure. There is nothing quite like the panic of a 2 a.m. maintenance window where a single missing route map deny statement brings down a 50-site WAN.
Only if you don't understand the protocol interaction. Let's explain the causality of how that loop forms and how we master it. The boundary router, let's call it R2, connects to both the MPLS provider and the internal DMVPN.
Okay.
R2 receives the exact same data center subnet from two places, from the MPLS cloud via eBGP and from the DMVPN router via internal EIGRP. Now we have to look at administrative distance, or AD. This is the metric a router uses to rank the trustworthiness of a routing protocol. A lower AD is trusted more.
Right.
eBGP has an AD of 20. Internal EIGRP has an AD of 90.
Meaning the router mathematically trusts the BGP route over the MPLS link more than the EIGRP route over the DMVPN.
Exactly. So R2's routing information base mathematically trusts the MPLS path. It installs the BGP route. R2 then does exactly what a router is supposed to do. It takes its best route and advertises it to its neighbors.
And there's the trap.
Right. If you don't redistribute carefully, R2 will take that BGP route and advertise it backward into the EIGRP DMVPN domain, poisoning the routing tables and causing a massive routing loop where traffic bounces back and forth between the boundary routers until the packets die.
Which is a disaster.
But to fix this, you must engineer the metrics. You use route maps to tag the EIGRP routes as they come in. You then apply a filter that says, do not redistribute routes with this specific tag back into the BGP cloud. Furthermore, you have to manipulate the BGP weight attributes to ensure that when the primary MPLS link fails and recovers, the network doesn't stay pinned to the slower backup link.
It's just so much overhead.
The complexity here is not a bug. It is the fundamental mechanism of traffic engineering.
Look, I see the necessity in that specific constraint, but listen to the sheer volume of mental gymnastics required just to return the network to its normal state after a failure. You're balancing administrative distance against BGP weight, applying tags, matching tags, and worrying about mutual redistribution loops.
It's engineering.
But if the system lets you make a catastrophic error easily because it has too many configurable knobs, it is fundamentally a fragile design. But okay, let's say we must rely on these interior gateway protocols to handle all this complex traffic engineering. We inevitably hit the physical limits of the hardware.
The CPU and memory.
Exactly. Eventually, the link state database grows too large, the shortest path first calculations consume too much CPU, and the routers melt down. Here again, I argue for predictable simplicity, specifically by choosing ISIS over OSPF for large-scale routing.
Now, this is where I heavily disagree with you. Both are link state protocols, but OSPF's strict area hierarchy is what physically protects the network from melting down.
See, OSPF's strict hierarchy is exactly its weakness. This is the core architectural trade-off. OSPF forces the architect to adapt the physical business to the protocol's strict rules. ISIS allows the protocol to adapt to the physical realities of the business.
How so?
Well, if we must scale, ISIS offers a vastly simpler contiguous design. In a new ISIS design, starting with a level 2 only contiguous backbone is incredibly elegant. You don't have to deal with OSPF's rigid mathematical requirement that all areas must connect directly to Area 0.
But Area 0 is what prevents loops.
At the cost of incredible complexity. You don't have to manage the myriad of OSPF LSA types, link state advertisements. OSPF uses Type 1 router LSAs, Type 2 network LSAs, Type 3 summaries, Type 4s, Type 5 externals, and Type 7s for not-so-stubby areas. It is a nightmare to troubleshoot.
If you don't know what you're looking at.
Furthermore, if an OSPF router generates an LSA that exceeds the interface MTU, the maximum transmission unit, the physical size limit of a packet on the wire, it fragments, and routers handle LSA fragmentation terribly. ISIS operates directly at layer 2. It's not encapsulated in IP.
That's true.
It's easily extensible with TLVs, type length value attributes, meaning you can just bolt on new routing capabilities, like IPv6 or segment routing, without rewriting the core protocol. It is just a cleaner, more predictable protocol to scale.
I wouldn't call maintaining completely separate link state databases clean. An ISIS Level 1, Level 2 boundary router has to maintain distinct databases for each level and run the SPF algorithm independently for both. That consumes memory and CPU.
But it scales better laterally.
I defend the precision of OSPF's complexity. Let's look at the mechanism of the full mesh topology example from the text. Imagine a 5x6 full mesh topology between major data centers. If you leave that in a single area, you have 1,800 different paths. The flooding would be catastrophic.
It would.
Every time a single link flaps, it triggers an SPF recalculation across all 1,800 paths on every single router in the domain.
Which is why you wouldn't design an 1,800 path full mesh in a single broadcast domain.
Exactly. You mathematically isolate it. You separate that mesh with an area border router, or ABR. By implementing an OSPF ABR, you reduce those 1,800 paths down to just 32 paths. You are using the complexity of OSPF area types to create precise flooding boundaries.
But you still have to deal with the LSAs.
Yes, you have to understand the LSA types, but that knowledge gives you granular control over what topology information passes through the network. When a Type 1 LSA hits the area border router, the ABR stops it. It summarizes that detailed topology information and hides it behind a simple Type 3 summary LSA. This mathematically prevents a link flap in Area 10 from triggering a CPU-intensive SPF run in Area 20.
But ISIS achieves the exact same flooding reduction with Level 1 and Level 2 boundaries, but without the headache of 6 different LSA types.
It's not quite the same, though.
It is. In ISIS, the Level 1 routers don't need a summary route. They just look at the ATT bit, the attached bit, set by the closest L1, L2 boundary router, and they use that single bit as their default route to leave the local area.
And that very ATT bit behavior causes suboptimal routing. Think about the mechanism. If a Level 1 area has 2 exit points, the internal routers will blindly send all external traffic to the closest exit based entirely on internal metrics.
Well, yes, but
They have no idea what the path looks like past the boundary. They might send traffic to exit A because it's 1 hop away, even if the actual destination is 10 hops away once it hits the Level 2 backbone. OSPF's complex LSA structure prevents that because it maintains the metric visibility of the external destinations. You acknowledge in ISIS that suboptimal routing is the required trade-off for scale. I'm arguing that if you embrace OSPF's complexity, you don't have to make that trade-off. You get immense scalability alongside optimal routing.
suboptimal routing is often an entirely acceptable trade-off if it guarantees the network remains mathematically stable during a convergence event. And I think that brings us back to the core of this debate.
It does.
Look, while I concede that a certain baseline of complexity is unavoidable, we aren't plugging 2 computers together with a crossover cable anymore, the primary goal of the network architect must be to limit fault domains. Whether it is avoiding the nightmare of mutual redistribution by migrating to a single protocol like Fastnet did, or utilizing loop-free Layer 3 routed access to completely eliminate spanning tree, minimizing the moving parts is what prevents the butterfly effect. If the system lets you make a catastrophic error easily because it has too many configurable knobs, it is badly designed. We need predictable simplicity to survive the inevitable hardware and software failures.
And I conclude that true network robustness is fundamentally tied to necessary complexity. An architect's job is not to run away from protocol interactions, but to master them.
Mastering them is hard.
But it's essential.
It is understanding how to tune multiple spanning tree to unlock bisectional bandwidth for live VM migrations. It is optimizing first-hop redundancy protocols to utilize all available uplinks, and surgically engineering route maps across BGP and EIGRP boundaries to extract maximum value and resilience from the infrastructure. A network stripped of its advanced features might be easy to configure at 2 a.m., but it will fail to meet the dynamic, stringent demands of modern business applications.
Well, I think we can both acknowledge a deep mutual respect for each other's architectural philosophy, even as we wildly diverge on the implementation.
Oh, absolutely.
Ultimately, we agree that the deciding factor isn't just an architect's aesthetic preference, it is the specific business requirement of the network. There's so much more to explore in the source material regarding these topologies, specifically how these interior gateway protocols interact with advanced overlay technologies like MPLS traffic engineering and segment routing.
We will leave it to you, the listener, to decide which philosophy should guide your next network design.
Exactly. Will your next design be beautifully robust or just a beautiful, simple paperweight?
Or maybe just a teapot pointing backward. Thank you for joining us on The Debate.